All right, welcome all. I went riding with a colleague on the weekend, and he asked me, so what is the grand goal of this lecture? And I said, oops, I think I didn't tell my students. Very bad. So what I want to do is I want to teach you the basic concepts and the jargon that you need to understand at least a good fraction of the papers that you see at today's computer vision conferences. And why do I say conferences and not journals? It is because in computer science, these conferences have really taken the role of the journals. So people try and get into the best conferences rather than in the best journals for a number of reasons, one of them being the rapid turnaround time. So within a few weeks, there is a guarantee day by which the review process is through, and you really get to read what other people are doing these days rather than, as opposed to 2 years ago. So last time, I argued that learning using an entire image is hard because images live in too high-dimensional space. And I was saying that, or I think I said that, on the other hand, just looking at single pixels is usually not helpful enough unless you have a spectral imaging device such as a satellite. And in between the single pixel and the entire image are the patches. So small rectangular areas of an image. And this is what we will talk about today. On the one hand, I will try and give a feeling for what you can and cannot do with patches. And on the other hand, we will learn quite a bit about denoising, looking at the very recent literature in the field. So when I last gave this lecture in 2008, half of the methods that I'm mentioning were just being published, and the other half was not even around yet. Okay, so this is pretty new stuff. So today, patches as the substrate of block matching, texture synthesis, and a number of denoising algorithms. So about block matching. Block matching is widely used in a number of fields. In stereo vision, in motion estimation or tracking, and in video compression. So if you watch a DVD or Blu-ray these days, part of what we're going to talk about today is used in such compression codecs. So block matching simply means we have a big image and we have a small block, and we want to find the best match of that small block in the large image. So as a case study, we look at video compression as used in MPEG 1 or MPEG 3. These protocols also comprise other strategies, but what we're going to talk about is part of those. What these codecs do is they, from time to time, transmit compressed still images. This is more or less what happens in normal JPEG compression. So in other words, the compression algorithm that your mobile phone uses when you take a picture, or most of your cameras, unless you have a professional device. And in the next weeks, we will look at the mathematical basis of JPEG, not as an end in itself, but because that's one everyday application. And then from you try to explain subsequent images or intermediate images in terms of these still images that were transmitted. So let's say we have time, and we can transmit a still image here and a still image at a later point in time. And then in between, we try to interpolate from the still images that were sent. And the interpolation is attempted in the following sense. As I sketched above, you try and explain each block in this interpolated image as a block either in a preceding or in a subsequent image that was moved to this particular point. So this works relatively well when there is little change in the scene, or there are actually more global transformations also, like if you have a camera pan and the entire image just seems to be moving sideways. But what I'm describing here is still one of the most frequently used mechanisms. So from time to time, you transmit these still images, and in between, you transmit with potentially sub-pixel precision motion vectors of matched blocks. And because you cannot perfectly explain in most cases an image just in terms of what comes before and what comes after, you also need to transmit the residual. And these residuals are again being compressed. So on the encoding side, you can compute the residual between the actual frame that you want to transmit and between a frame that you obtain by simply explaining it in terms of motion vectors with regard to a preceding or subsequent frame. So let me call this the motion reconstructed frame. So there are a number of steps. Patches have a different name in different communities. Here they are called macro blocks. So what you first do is you partition your image into macro blocks, which are just patches, and typical size would be 16 by 16 pixels. You then transform to a different color space and the one that is used in this field is a representation where you have a brightness channel, which is visually the most important one, and then you have CB stands for chroma blue, and CR stands for chroma red. And what these code for is a surplus or a deficiency of this specific color, in this case of blue, with respect to a pure gray image. So if we had CB and CR set to all a constant value, so for every pixel in the image, then Y prime alone would encode a gray value image for us. And CB and CR give for each pixel if with regard to purely monochromatic image we have more or less of a specific color in there. So this is another way to encode colors. you can obtain this with a linear transformation from RGB. And well, if you simply transformed it, there would be no gain and no loss. But it so turns out that brightness is perceptually much more important than the colors. And this is why these chroma channels can be subsampled. So I'm showing here in black the locations of the pixels for which we encode the brightness. And then the red, for example, is only transmitted for 1 out of 4 pixels at a location that is interpolated. And similarly for the blue information. And by the way, if you re-watch this lecture on YouTube afterwards, you will see that the red and blue doesn't, if you watch it at strong compression, you will see that the colors don't come out as nicely as they do now. And that's for the very same reason that at low bit rates, the color is ignored if it does not span larger areas in the image. So at strong compression, my blue and my red dot, they will look rather grayish. So the reason here was that humans are more sensitive to variations in brightness than in color. So at least when we talk about high frequency variations. By high frequency, I mean patterns that span few pixels only. Question is if the sampling mesh is the same. In general, yes, it's the same simple pattern that I'm showing here. There are also octree type partitionings of an image, but they have not found widespread use. All right, then for the match, we need to define a similarity measure, of course. And one popular choice is the sum of absolute deviations. Which will give me the quality of the match between a pixel located at coordinates x, y at time t and a pixel located at uv at time t minus 1. So IT is the intensity of the image at time point t at the locations which I'm indexing here. So UV here, not absolute locations, but a shift. So this was the sum of absolute deviations, and similarly you can define the mean squared error or sum of squared deviations, and then there are windowed versions thereof. So SSD would be the sum of square deviations, which up to a normalization factor is the same as the mean square error. Which you obtain if you use the L2 norm rather than the absolute differences here. And then there are alternatives to all of the above, which take into account more edge information, for example. Okay, so now we've chopped up our images into patches, into macro blocks. We have computed, we've transformed to different color space. We've subsampled a little. We have a dissimilarity measure, and now we actually need to do the real work to find one patch in another image. So we want to search the blocks of the reference image. In the current frame. If we do this naively, so if we try and match each block from my reference image to every possible location in the current frame, this is going to be too slow. So we need to think of speedups here. And I would like to have your suggestions for this. Great. So you've summarized 50 years of research or so. So what you are suggesting is rather than an exhaustive search, you want to do some kind of greedy strategy, which in this field is also called a partial search. So one good possibility is to conduct a partial search. And many papers have been written here with different suggestions. One popular technique is so-called diamond search. Diamond search, or DS for short. So this is when I talk about jargon, you know, there are so many abbreviations and so on. A lot of learning. Okay, so let's say we have a reference block, and in diamond search, we start putting it at a number of possible locations in my current frame. And I'm putting ones here to indicate that this is iteration number 1. And I will copy this because we need to distinguish two cases here. And I want to describe the other case in a moment. Okay, so case 1. Let's say case 1 is that we compute the sum of the absolute deviations at each of these positions, and the lowest distortion was measured at the central pixel. The funny pattern that you've seen here has a name. It's called the large diamond search pattern. So what I wrote here in black was the large diamond search pattern. And you want abbreviations, I give them to you. So seriously, this is what it's called in the field, LDSP. And in case 1, that the lowest distortion was found at the central pixel, I then switched to the small diamond search pattern, which looks like this. And case 1 was the case where the smallest distortion was at the central location of my LDSP. Okay. Now it's evaluated at these additional positions, and if you so wish, you can then refine this and do it even at subpixel positions. But let's look at case 2. We have the smallest distortion at one of the peripheral locations. Of the large diamond search pattern. Let's say, for example, here. And I now continue in the second round by saying the point that I circled is now my new central point, and I now want to find the same kind of pattern that I have just drawn around this new central point. And one beauty here is that this large diamond search pattern has now been moved to a different location, and I've only needed to recompute 5 out of the 9 locations. The others can be reused. They are stored. Okay. Now let me do one more iteration here for illustration. Let's say the new minimum is here, and I want to center my large diamond search pattern at this position here, which will give me a 3. I have all of these already, and here. In this case, I needed just 3 additional evaluations. And I again find this kind of search pattern. Okay, and this is continued until the lowest energy position lies at the center of the search pattern, at which point we switch to the small diamond search pattern here, for example, in iteration number 4. So this is diamond search, and many alternative strategies have been published, but this is the one that won all the benchmarks up to the turn of the millennium, and because this is when many coding committees were working, this is what's used very broadly nowadays. Yeah, exactly. The distortion measure is what I previously here called dissimilarity measure. Typically in video coding, the sum of absolute deviations. So I think you will agree that all of this makes sense from an engineering point of view, but it's not exactly rocket science. The feeling I share. So there's, like in so much of image analysis, there's unfortunately no Schrödinger equation to be solved here, simply because human perception is not described by any simple equation. And this is why video compression is not what I would like to call a first principle science. Because the ultimate quality metric is how good a human thinks the result is, and unfortunately humans are hard to summarize, or maybe not unfortunately. Fortunately, humans are hard to summarize in equations. So the aim of all these compression algorithms is to trick human perception. So to use as few bits as possible in reconstructing an audio signal or a video without the human complaining too much. So in particular, if you look at, let's say, image compression algorithms, the sum of absolute deviation or the mean squared error, those are very poor measures of what humans think is a good compression or not. Not least, let's say if you have a squirrel sitting on a rock, then typically, unless you're a geologist, you care more about the cute squirrel than about the details of the rock. But if we just compute measures like the peak signal to noise ratio, one algorithm may win over the other because it did better on the rock, even if it messed up the squirrel. So there is still room to improve all of these algorithms, I believe, but not using such simple error metrics. And this is why people are now trying to use or to develop metrics that better reflect what humans think looks good or not. I wanted to give you further examples of where such block matching can be used. So here's a pretty image from Australia. These people studied turbulence, and they do so by means of particles or beads that can be suspended in a fluid or in a gas. The perfect tracer will be very distinctly visible. So typically something that fluoresces well. It should have the same density as the surrounding medium, so it does not experience buoyancy or does not feel gravity. You would ideally want them to be very small, almost massless, so that, what's the word for this? So that they won't, give you a distorted picture of the phenomenon that you're studying. So what is this called in English? Mass times, so Trägheit in German. Yeah, you want particles with practically no inertia, so that you will really study the motion of the fluid or the gas and not the ballistics of your particles. And this is an important experimental technique to study flow phenomena, turbulence, and so on. And there are two distinct kinds of approaches. There is particle imaging velocimetry, which uses just the kind of block matching that I've just described. And in contrast to that, there is PTV, or particle tracking velocimetry, where you really try and follow each and every particle individually while maintaining their or keeping track of their identity. That is a harder problem than simply finding matching blocks. Can you think of a trade-off here? What happens if blocks are too small or too large? Yeah, if they're too small, you will get ambiguity, exactly. And if they're too large? Yeah, well, here the point here is not compression. Here the point is more to establish these motion fields. And what I'm showing here is an actual photograph with long exposure time. It's not the motion field as such. So what people did here is just that they looked at these fluorescent particles and used a really long shutter time to produce this image. But what you want to get out, because that is a pretty image, but it's not a motion field. So what you want to get out is an image where you have, for each patch or for each pixel even, a vector pointing to a different location. So what will happen if the blocks are too large? Yeah, very good. Very good. So let's say we look at a big wheel that's spinning. It's rotating in this direction. If I use a small enough search window at one time frame and the next time frame, I can find the search window again and ignore the fact that actually there was rotation in the image. But if my block is too large, my patch that I'm trying to match is too large, then the rotation of the phenomenon will mean that you get a poor match. So there is that. And then obviously also if the blocks become too large, you're going to smooth over the fine structure. So here you see some pretty small vertices. And if you made your block really large, you would lose them, of course. You would smooth away all these interesting structures. Okay. Now I've been glossing a little over the many parameters that there are. And I want to show you a video. So the blog of Martin Paris, and he has this video where he is showing, so he's written a GUI and he's showing the impact of different parameters. Here in a stereo matching example, you see on the top two images that were, well, I will stop this so you can listen. At least I get always totally distracted if I see things moving. So you see at the top two images that were taken by the left and by the right sensor of a stereo rig, and the task is to estimate the depth. And you can do that from the disparity map. So things that are close by, if you hold your hand not too far from your eyes and you look through the one eye or the other, you will notice a large shift. Whereas things that are infinitely far away, they will not shift at all. So the amount of shift translates to the proximity. And one way to do such stereo estimation is by using block matching. Now, we have all these different possible parameters here. For example, it is possible to, especially when you have very noisy images, to pre-smooth the block that you're going to match. There is the important parameter of how big are the blocks that we are comparing, number of disparity levels to be estimated, and so on. And he's playing with these parameters one after the other. This is all real time. It's a very fast algorithm. And you can see that, depending on how you set them, you get something totally nonsensical, or, at some point we already saw a nice depth map being produced. Okay, so here you can see, let's stop the video here, to go into the break with something, optimistic. So you see the lamp here is relatively close. There's the head, and the background is further away. So this works okay. Now, it works okay, but it's still noisy. And this is why you need regularization in addition. And we will, in the last weeks of the semester, we will spend a lot of time talking about different regularization strategies. So how you can get rid of the noise without over smoothing your image. And this makes for mathematically quite hard problems. And there are, on the one hand, cheap heuristics to crack these, and then on the other hand, very fancy algorithms, and we will discuss both. Right, that's what I wanted to say about block matching. If you care to read about it, there are many sources, of course, but I wanted to point out this tutorial here by Rick Salisky, which is the nucleus of a book that he has written later on, and this covers much more material, also more things that we will talk about later this semester, but amongst other things he mentions also this block matching more in the framework of stereo estimation than of video compression. So that was block matching. I've shown you an example here of how it's used in stereo, and as you saw, the algorithm is very can be implemented very quickly, which is why this is something that's really running in cars nowadays. So if you buy a fancy car, you get to something that will warn you if you're about to run into something or into an obstacle. And cheap algorithms or fast algorithms like these are being used in such automotive applications. We've talked about video compression, and to give an example from motion estimation, I've shown you on the one hand this particle imaging velocimetry, and if you remember the digital embryo data I showed you last week of this organism with all its cells unfolding and dividing and so on, we're actually using that kind of strategy there as a pre-processing step before then tracking individual cells along with their identity. Do you have questions for this block matching part? Okay. Then after the break, I want to talk about texture synthesis. So texture is the word we use when things somehow look repetitive and the identity of individual objects doesn't matter too much. So if you look at people from close by, it's a group portrait. And if you look at 50,000 people sitting in a football stadium, this is a texture. And patches play a big role in synthesizing such textures. But before I explain to you a very nice algorithm that does extremely well on examples such as these, in the break you can think a little bit about how would you synthesize textures. So given these examples, how would you synthesize an image 10 or 20 times that size, which looks similar without showing too many artifacts?